Alright, to the whiteboard review, and this was today, okay? CIS-125, and today is the 14th. And we're talking about the design process. So to start off with, we looked at, actually started off the day, drew a box and asked, what is it? Okay. I didn't get a roaring response, but anyway, most people are getting to the point where they understand that is a process box. This is a decision box. Here's another process box, but since we were initializing a variable, we also now have added initialization box, where we're taking a variable and assigning it a value. Limit equals 100. Initialization. We reviewed an input box, which can also serve as output boxes. Down here we have an example of the parallelogram being used as an output box. Decision box. You have a true direction, false direction. Doesn't mean you actually have to do something on both sides. You have those, and it always comes back together. Always comes back together. One in, just touching, and one out. Make sure your lines are flowing down and to the right. We talked about that. Process boxes are the same way. One in, one out. One in, one out. Same thing here. One in, one out. One thing we didn't show on this diagram, the oval for the start and stop. All programs need a start and stop. And I was really pleased. A lot of students were saying, yeah, you got to have this, because they are working on their checklist. So over here we have a flow chart, and then over here we wrote the same thing in pseudocode. So we have action word, action word. Boy, that green from the screen turned out funky on my iPad. Initialization is the action word. Here we have an action word. A couple things very important. This is a nice straight line. Okay, nice straight line. These things are all lined up because indentation makes a difference in our design. So here we have an action word. Calculate on the right, store to the left. And here we have a conditional. If C is greater than the limit, and the limits in the legend, just like pi, radius, circumference, they're all defined in the legend, all those variables. If this is true, we do the part right underneath. If it's false, it skips that and goes down here. If-then structure. Always comes back together, and here it goes. So it's this same structure right here. So we were supposed to be able to make the relationship between pseudocode and flowchart. I mentioned at the legend. I think I'll go to the next page. Same thing, just a little bit bigger. Let me emphasize a couple points here. All this lines up. True, false, if, then, else, and if. That's the structure. So that's the same structure as you see here. If, then, true part, false part, and they come back together at the end if. These are process, initialization, input, output. These here are actually output. So we can represent a solution as a flowchart or represent it as pseudocode. And hopefully you can see these relayed up here. Make sure you can see that. This one's right there. The decision is is right there. True part, false part, and if come back together. This, by the way, you can draw a line and connect it to a box and give a more thorough explanation of what that box represents in the flowchart. And here, I want to emphasize the legend. Okay, so in the program, you could have done one of two things here actually. Here, I would just use the letter C and make it a little bit easier. Remember, we calculate here and store there. Or you could have here used the word circumference, you know, if you wanted to. The other day, instead of just an R, here we're using an R, you could just use, the word radius. For variables, it's actually nicer to use a more descriptive name. More descriptive name. And then remember at this point too, right, variables, we're either talking about them being a string of information, or maybe refer to that as text, or they're a numeric, a number representation. These are numeric. Radius, that's going to be a number. Circumference going to be a number. Pi, so this is a floating decimal, and when you do the calculation, that'll make this a floating decimal. If the radius had a decimal in the number you entered in, then that would be a float too. We talked a little bit about declaring, okay? Declaring variables, and we'll do that a little bit in Python later on. So this, in a way right here, when you initialize pi to be 3.1, you actually kind of declared it. You forced it into being a floating point variable. Math-wise, that'd be like a real number. Okay, it's going to have decimals, and it's going to figure out where the decimals belong. Iteration or looping, we have leading decision. Okay, we've got a connector, we come into the connector, we come into the box. In between here, no processes. No processes. You shouldn't have any boxes in between there. Okay, then down here you have all your work, and then you can loop back up and do it again. It'll keep looping as long as your condition is true. Over here we say do while, and then we have the condition, and then we indent, and we do these particular things right here. Whatever lines of code to be in there. And you could have anything. You could have decisions. You can have sequence, you know, different things in there. And then this will keep looping until this becomes false, and then it goes here. A do until as a connector, then you do all the work, and then you decide. If this is false, more or less get out. If you want to get out of the loop, and it's true, this gets you out of the loop. If not, you go up and you do this work again. No processing in between here. No processing from this point up to here. So that's a do until. We've got a condition. We do what's indented, sends it up, okay, sends it back. It's actually making the decision down here, even though we don't write it that way in pseudocode. But it actually makes the decision down here. And so here it stays in it if it's false. Here we stay in the loop when it's true. I reviewed a couple key points about, you know, our software, our programs. If they're executing, they're in memory. They're moving back and forth between, takes an instruction, gets it processed, sends information back to memory, takes instruction, processes it, sends information back to memory. Before we execute the code, it may be stored on a local hard drive or in storage. Opcode, case structure, last one we talked about, the last structure. Based on this in here, this operation code, if it matches what's here, then it does this. If it matches what's here, here. If it matches what's here, here. If it matches what's here, here. And then this is, if none of them match, then it goes to the other. Does this work, and then it exits. One in, one out. And it's only going to execute one of these. It's going to pick whichever one that matches. So this could look at days of the week, and then this variable here, what could be here, would be Monday, Tuesday, Wednesday, Thursday. Maybe a Friday and then other, or whatever. Or it might be a menu selection, or it might be a tax bracket or something. Okay. The pseudocode would look like this. You'd say case entry, and here's your opcode. If that opcode matches this, then it does this code. If it matches this, it does this code, and so forth. If it doesn't match any of them, it does the other. And here's the end case down here. So it enters and then exits down here. That's the last of the top-down design. We talked about designing from the top down. You analyze and develop and make sure you have everything right before you actually code. Bottom up, we talked a little bit about that. Bottom up, sometimes it's called rapid prototyping. The idea you create something and then you build on it until you get up here what you want. Here you say, this is what we want, now we're going to take the steps to make sure we get it right. Here we start building and we end up here. This can be great as long as you can afford to make some mistakes, or you can afford to maybe not having it cover everything. If it's a situation where you can't make a mistake on one of the stages, then top down's a better way to do that. Top down, bottom up. So top down analysis, actually analysis, design, develop, and implement. Okay? Those are the four major things. If each one, the better that it's done, the better you go through these steps and make sure you do a good job here, the better you're going to be here. And then in the design, if make sure you cover all the steps and do a good job here, then development will be easier, be more accurate. You'll end up with a better product, and so forth. So I spent a fair amount of time talking about this up here today. Define the problem. You got to understand the problem. You can't solve a problem if you don't understand it. Our problems will exist around, we're saying, yes, we need this solution, we're going to put this in, can the computer do the processing to figure that out? Input, process, output, IPO. We need to figure the IPO out first. You know, do this by hand. Can we do 1 or 2 records by hand, or 1 or 2 pieces of data by hand, and see if we can get the answer? Once you're pretty sure you understand that, then you can go to the next step and you can design the solution using flowcharts, pseudocode. Have self and peer reviews of your design. You can walk through your design to make sure it works. Then you can write the code. We'll be writing in Python version 3. Get people to self-evaluate it and do a peer evaluation. Make sure you have it working. Test and development. You know, our code implementation would be pretty much making sure it works here in our environment. And you evaluate, is it producing what you want? More or less you go all the way back up here. is this an efficient way to get to this solution? Was this a good way to do it? I mean, if we're not getting the product that we want, then we have to make some changes. And then there's always maintenance, you know. If you find something isn't quite right at this point, then you go back up here, you understand what's not right, you figure an IPO on it, you design the next solution, you develop it, and then you send an update to you implement the update. Okay, so this is really a cycle. Get it? I'll do it in green. You start up here, you get your software working, and then you do an analysis of it and make adjustments, and you keep making a circle until the software becomes obsolete, and then you start over from scratch up here. Almost done. Software gets too complicated to write huge programs, so we split them into modules. A module just to handle maybe the input of the data. Okay, a module to do X, Y, Z, and then another module that maybe stores the results. Maybe, I don't know, another module that does any reporting, etc., etc., etc. Then we put all those modules together. We make a main line that calls all these modules and gets to do the work. This is really a big deal because it's just an example, in Python, there are a ton of pre-made modules that do a lot of work for us, like sort and array. That may not make a lot of sense now, but you'd rather have a module sort an array than you trying to write a part of a program to sort an array. Okay? And do we sort a lot using technology? All the time. And then I want to clarify here, we have to do a little work with this as a whole. We take the source code, this code now we write after we do all these steps above, you know, all the design and everything. And then we get to where we can write the code, we can compile it into an object code, and the object code then can be linked in executable code. The linking can bring in all kinds of modules that are already pre-written to allow us to do certain things we wouldn't want to write ourselves. Okay? Some people even claim good programmers nowadays do half their job, or more than half, is discovering which modules they can use to do certain tasks. Okay? So, I think we're good rather than, alright. So, to highlight where we've been, okay? Understand the problem. What do you want to solve? You know, can you figure it out by hand? Okay? Can you figure it out by hand? Then you're going to design a solution. Flowchart, pseudocode. Okay? Right now we're going to do both. In the future you can pick one. Okay? Then, once we're sure we've tested this, did some walkthroughs and so forth, we're pretty sure our design is good, then we can go ahead and code. Okay? Using Python. Your design should have taken care of any logical errors. So here, you'll be concerned about the syntax of the language. After you get the encoding, you know, lots of testing, making sure it's working, trying, you know, using good test data. And then you finish up your documentation and go on to the next project. Alright, that's it.